Now that we have, a general or heuristic idea of what we mean by a limit and some useful properties of limits, the next step is looking at specific examples and techniques that we can use to actually find specific limits for specific functions. So when you're working with a rational expression, the first thing you should do is apply in one of our rules from the last lecture that says we can just substitute 1, the limiting value here, into the top and the bottom. And when we replace the x in the denominator with 1, the whole expression simplifies to 0, which is a problem. Remember that this was the exception in the last property that we discussed in the last section. You could only take the limit of the top and the bottom separately when the bottom doesn't equal 0. However, the fact that the function doesn't exist at x equals 1 doesn't mean the limit can't exist. Now remember that when we talk about limits, we're only concerned about what's going on around the point. So before we say the limit doesn't exist, the first thing you should always try to do is simplify the function. In this case, the numerator and the denominator both factor, making the function, the expression, rather. And now the two x minus 1 terms cancel, leaving us with this. Now this function isn't undefined at x equals 1, so we can find the limit just by simple substitution. Then when we simplify this, we get that the limit is equal to 3/2. Now, to get a better idea of what's happening here, I think it helps to look at the function's graph, the graph of 5x squared minus 7x plus 2 over x squared minus 1. So this is what our graph looks like, but because the original function is undefined at x equals 1, that's why there's going to be this hole at that point. And now you can see why the limit exists, even though the function doesn't. As we get closer to x equals 1 from either side, the y values get closer and closer to 3/2, even though they never actually get there. Now, this limit is another case, like the previous one, that's undefined at the point we're interested in. That is, if you substitute 3 for x, the denominator becomes 0, and the function is undefined. Now, unlike the last example, there's nothing we can do here to simplify away the x minus 3 factor in the denominator. And if you look at the graph again, you can see what's going on. You see that as x approaches 3 from the left, the function is dropping down to negative infinity. And as x approaches 3 from the right, the function is going up to plus infinity. But those aren't the limits. If you go back to the definition of a limit, you'll see that they have to be real numbers, which plus or minus infinity aren't. So in situations like this, our final conclusion has to be that the limit doesn't exist. Now, the result here is essentially the same as in the previous question. The function's undefined at x equals 3, and there's nothing we can do to simplify or fix that. However, there is a special circumstance here that we need to discuss. The graph of f of x equals 1 over x minus 3 squared looks like this. So what makes this situation different from the previous one is that x approaches 3 from the left, and as x approaches 3 from the right, the function appears to be going to the same place, plus infinity. Now, in situations like this, the generally accepted rule is a little confusing. On the one hand, we still have to conclude that the limit doesn't exist, because limits have to be real numbers. However, even though it seems contradictory, it's also generally considered acceptable to write the limit as x approaches 3 equals infinity. Now, this is a situation that we can simplify using our exponent properties of limits. Remember, a square root is the same as raising the base to the 1/2 power. And our exponent rule says that we can bring the exponent outside the limit. Now the inside is just a polynomial. So the limit becomes the square root of 5 minus 4, which is just 1. All right, now this one is a little trickier. If you substitute 4 into the function, like I essentially did in the last example, you get the square root of 4 minus 4, which is just 0. And this could lead you to believe that the limit is 0, but you have to be a little more careful. But remember that the exponent rule for limits had the qualification if the limit exists. And again, I think it helps to look at the graph to get an idea of what's going on. The graph of the square root of x minus f of x equals the square root of x minus 4 looks like this. Now, if we try tracing the function as x approaches 4 from the right, you can see that the function is approaching 0. However, if you try to approach x equals 4 from the left, you can't, because the function doesn't exist on that side. So there's no function or no graph for us to follow. This means that the limit as x approaches 4 from the left doesn't exist. So even though the limit as x approaches 4 from the right is equal to 0, the limit doesn't exist, right? Because the limit doesn't exist on both sides of 4. So we have to conclude that the answer to the overall question here is that the limit doesn't exist. Okay, so in the next lecture, we're going to kind of continue looking at specific examples, and we'll look at the processes for calculating limits at infinity, and we'll look at what you have to do to calculate the limits of piecewise defined functions.